I want to share my recent research with you. Sorry that I cannot, due to some schedule conflict, I cannot go to Santa Clara this April. So that's why I do this recording and hope that you can still give some comments after you listen to my talk. So today I want to talk about active learning techniques in interactive machine learning. So as you can see that active learning technique will be one of the focus, but beyond that we will also talk about interactive machine learning that can be realized in a smart factory scenario. So here is our outline, and in the past few years we talk about we have spent some tremendous efforts on the research of IoT and data analytics. So we have been working on several different applications such as transportation and smart building and smart factory, etc. So between those different applications, actually we ask for a common foundation that we call continuous sensing and monitoring. So by that, what we mean is that a system can continuously collect data from the environment, and by analyzing the data, we know what kind of state that we are in, so that maybe we can do some reaction with that particular states. Continuous sensing and monitoring, to realize that we need to continuously work on something such as that we continue to collect data and do some pre-processing and do some analysis, and sometimes the analysis and evaluation must be done in real time so that we can instantly react if we have some emergency situation. So the challenge that in data analytics in this situation is that, of course, we are going to have some difficulty when deal with IoT analytics. And other than that, sometimes we are going to have large-scale data, so that we also need to pay attention to the big data issues. And other than that, and we need to think about, for most IoT-related data, that we have spatial and temporal dependency. So usually that we need to pay attention to those dependency, those relationships, so that the analysis can be enhanced. Okay, so think about that. We have such a different continuous sensing and monitoring based on those different sensors that we can collect a lot of information. In the past few years, if we have spent some efforts on ITS, especially that we talk about traffic forecasting. Okay, so the problem is quite easy, right? So we have a huge amount of historical data, such as the data that consists of several years or maybe up to 10 years or so, right? So in this research, actually we have been working on just those tremendous amount of data. We hope that based on those historical data, and we can predict for the next moment what kind of traffic status that we have. Okay, so problem is very easy, that we have several data collecting as time goes by, and we want to predict what could be the state in the next moment. Okay, so what we try is to use a Gaussian process with several complex patterns considered, so that actually in the end we have a very good performance. Okay, so to be more specifically, we talk about several different aspects that we can observe from the data, such as that maybe the data will have some temporal relationship, data will have some spatial relationship, such as that the sensory data collected from different locations, that we can observe different traffic status in different locations. So sometimes when we have some downstream traffic jam, then after a while that we also see the similar traffic jam in the upstream. So that's what we can say, that the spatial dependency right here. And also, sometimes we are going to talk about the several features, such as that for the traffic data, we have traffic speed, occupancy, and flow. Those different features may interact with each other. What we mean by that is that they will have some correlation, and those correlation, if we consider those, then the prediction will be better. So if we focus on the temporal dependency, we'll also talk about the long-term dependency and short-term dependency. And then if we talk about the long-term dependency, there will be some different periodicities involved, such as that for the traffic data, we're going to have the daily periodicity and the weekly periodicity. That all we can imagine. So this study actually we have been using a Gaussian process as we just described, and then combined with several different aspects such as daily and weekly periodicity and also some date short-term behavior. Then combined together, that we can predict the future, such as that if we want to predict the traffic speed, then we can have the MAE, means absolute error, equal to about like less than 1.5 miles per hour, which means that the true value is that, say, 41.5 mile per hour. Our prediction could be 40 mile per hour. I think that the result is good enough for the real application. So we also compare our model with some other well-known models such as V-ARIMA and also some other well-known models such as support vector regression. And what we can have quite confidence is that actually what we can say is that our result is much better than all the other methods, such as that some other people also used the hybrid spatial temporal modeling, and their performance is not as good as we have. Okay, so if we want to, that's what we have in the work I just described, that has been published in IEEE Intelligent Transportation this year. Okay, and when we move on from continuous sensing and monitoring to interactive machine learning, so we can talk about the following. So we continuously to have some data collected as time goes by, right? So and then we continue to build model, actually a series of model, and the model will be adjusted according to different, maybe that we call seasonal factors also, right? And the model will continue to perform well, particular to data that we collected at some different moments. And other than that, we also have the human that continuously give us some inputs, okay, some hints, such as that maybe usually that we can say the human will give us the label information to train better and better model as time goes by. Okay, so what we want to emphasize is that if we want to, let's say, talk about online, here is that we can say it's online learning, right? But what we want to say is more than online learning. We want to evaluate, or we want to analyze that the human factor in this learning loop is not as simple as that what we expected before, such as the human labeling, for instance. Human labeling may not be consistent. Human labeling may not be always reliable or available, etc. So we want to put more focus on this part. So we talk about, okay, between, let's say, machine and human, so we have interactions in between, so that the human continue to give some hint to machine, so that the machine will learn better and better. And on the other hand, machine will also tell human what's going on, so that the human may feel satisfied with the machine's performance, or maybe not. And then the human will continue continuously to give feedback to the machine. Okay, so after a while, then we hopefully that we can have a converged result, meaning that both the human and the machine will perform better than before after a certain period of time. So we just emphasize that the human can help in this learning loop, right? So on the other hand, humans' effort is not always reliable or trustworthy. So we want to evaluate this part. When we talk about interactive machine learning, so we have several similar concepts in machine learning category. So such that we can talk about semi-supervised learning, active learning, online learning, and reinforcement learning. So actually, Professor Lee, when he is in Santa Clara, he mentioned about there'll be the major difference between interactive machine learning and all these disciplines, such as that actually for the interactive machine learning, we can evaluate humans' efforts, such as that when the human labeling is not trustworthy, when the human labeling is may involve different costs due to the different people with different ranks, such as in a smart factory. Then when the different people are asked to label the same thing, they may have they may be associated with different costs, and also the human labels may not always be reliable. So we want to take those factors into consideration, so that when we have the human and machine talk about at the same time, we can be able to take all the things under one, to combine all the things together in just one framework, so that we can have such consideration and make it to be possible. Okay, so just to keep in mind that we hope that after a certain period of time that the machine will learn something from human, and human will learn something from machine. That's the basic idea of interactive machine learning. So in the first phase of this project, actually we have spent some efforts on active learning techniques. We have developed several algorithms, and of course the active learning algorithms can be used in the active machine learning scenario. So the active learning technique that we have been discussed many times. So basically, so we continue to have some input coming, and that input would mean unlabeled data X. Unlabeled data comes to us, and then we can decide either we want this X, and maybe we consider this X is quite informative. If we can have the label information, then we ask the oracle for the label, and otherwise we just include it without the label. And in some other occasion, we can even consider those X will be like noisy data. We can just simply discard the data. Okay, so we can continue to do this loop, and hopefully we can build a better and better model as time goes by. So the first research that we have been doing is that we call the active learning and dual supervision research. So we talk about that most active learning research, they focus on the instance labeling, and actually we can also talk about feature labeling, such that if we can start from the text data, and we talk about from time to time we can ask the human to help us label some text, such as this text could be considered related to the concept of baseball. Okay, so the human usually need to finish all the articles so that they can decide that it's related to baseball. On the other hand, sometimes we also observe some keywords such as home run and center field, and then we very quickly that we know it's about baseball. Okay, this article is about baseball. So in this case, that actually what we prefer is to label the keyword. Okay, so if we can label the keyword, as soon as that we see the keyword, we very quickly that we know the article is about baseball. Okay, so when we are given a huge amount of data, if we see many articles that have the, for instance, the center field or home run, then we know that they are about baseball. Okay, so by having this, very quickly we'll have a lot of information, On the other hand, on the human side, actually, the labeling is quite cheap, because when humans are asked to label one keyword, they can almost like take no time to answer this kind of question. So that's compared to label instance, label text, that takes several moments to finish. So we have proposed a unified approach so that the input data either will have some instances or features that they can all take into consideration in a unified formulation. Actually, by this unified measure, and actually we can say that either in some particular moment we want to label an instance or label a feature. Let's just want to consider that when we want to ask the label information from Oracle, okay, so we have to consider that how to incorporate the feature feedback, or such as that the label data should be considered. We talk about is that maybe we can find a way to synthesize labeled feature and make it to be labeled instances. And on the other hand, we can also borrow the experience from information gain, such as the decision tree usually use information gain to decide which could be the most informative feature. But in this case, we don't have all the label data available to us. So we have to find a way to deal with this situation. On the other hand, we also need to talk about for the non-text data, and we also use the similar idea. So here is some example to illustrate our idea. So think about the activity recognition scenario, and maybe in smart home, we want to, let's say, let the machine know what kind of activity a user is at some particular moment, or maybe the human can always answer, I'm now doing some exercise, I'm now eating, etc. Right? So that is what we consider give labels to instances. Other than that, sometimes we can also consider the following, such as that, okay, maybe the machine asks a human what you are in, what kind of activity you are in, and the human will going to reply that, okay, I'm always eating dinner when I sit in front of this table. Then what it means is, what the user means is that actually the location is very important to decide activity, which means that if we know the location is near this table, then we almost can conclude that the user is eating at that moment. Okay, so that's one thing that we can say the location is a very important feature in this case. On the other hand, the user may reply that I'm always eating at 7 p.m. So in this case, the time is a very important factor. So meaning that maybe we say using the time feature that we know what kind of activity the user is in. So from time to time, we can use several features like this, like time and or location, to decide the activity. Okay, so meaning that label features will also be important for non-text data. Here is some model details. What we want to say is that when we transform the labeled features, the label feature is going to transform to some synthesized label instances, meaning that there will be many labeled instances in the space, but proportionally to the possibility that we can observe from, let's say, from what we mean by that is that for different instances, maybe they will be associated with different ways than when they may have observed features, the labeled feature in the instances. So we have talked about, we have worked on the non-text data, and actually from the UZ-11 data set, we have collected the mushroom data set and trace data set and also hard data set. They are all the categorical features. Okay, so by having that, we can use to say, okay, to label the feature will be informative to decide the final label. Such as, maybe we can give an example such as that if we want to check this mushroom is poisonous or what, then we can say, oh, then somebody will reply that, okay, color is very important feature, right? So then we say if this mushroom is colorful, then we say this mushroom is poisonous, right? We can say, okay, in this case, the color is an important feature. Maybe we can better to, instead of label instances, we can also label this color feature so that we can very quickly conclude that many kind of feature, many kind of mushroom will be considered poisonous. Okay? So to analyze these few data sets, actually we have very good results such as that. So actually those will be text data that we can observe that between the solid line, that is that when we have the feature labeling, and the dashed line means that we don't have the feature labeling, and we were going to see a clear gap in between. So maybe you consider those gaps will be very small, but actually what we talk about is the y-axis is from almost like a 0 to 1. So the gap is actually could be considered a little bit less than 10% in difference. And there'll be the performance on the non-text data. As you can see that we also have a clear gap in between. We include the feature labeling and we don't have the feature labeling. Up to now, we talk about we can analyze the text data and the non-text data. For the non-text data, we can talk about when we have the categorical features, we can use the same active learning framework to deal with it. But if we talk about that, there'll be tremendous amount of data that they only have numerical values. So how to deal with that? Actually, recently we start to work on this part. So for the numerical features, actually we will consider transformation that is called the vector quantization, and we can use vector quantization to transform the numerical features to categorical features, and then maybe we can try the same trick with the categorical features, and hopefully we can see good performance from there. So I think vector quantization means that basically it's a technique to transform the numerical signal to digital signal. I think it's a well-known technique, so we are going to skip this part. So another research that we have been doing is that what we call active learning with massive high-dimensional data. So on this part of research, we are thinking about that if we have a huge amount of data, and also the data could be in high-dimensional space, how to perform the active learning technique so that we can still enjoy very efficient active learning procedure. So we can use this formulation to write down the time complexity, that the time that we need to spend on active learning. So active learning is actually the time that we need to spend on active learning consists of two parts. So one is that we need to train our model on each iteration, right? And also we need to consider that from time to time we need to do some re-ranking, okay? And re-ranking means that each time that when we collect more unlabeled data, and we need to rank the unlabeled data according to some predefined measure, so that we think that one data could be more informative than others, so that we have to know its label information. So how many times that we need to do this, that we call the uncertainty computation, that is the issue. On the other hand, how many times that we need to do the re-ranking after we have the uncertainty computation, that's another issue. And also after all, that we need to perform sorting based on the rank result, okay? So consider all this, and then we are going to say, can we reduce the time based on those considerations? So first of all, we are going to say, okay, how many times that we do the re-ranking, we try to make it as small as possible. So basically what we mean by that is that sometimes the model may not change too much, right? So that if the model doesn't change too much, then the ranking based on the model will not change too much. Then maybe we can say we don't need to change the ranking. At the same time, just because we don't need to change the ranking, then we can save the time on the sorting tool. Okay, so first strategy is that, okay, we are going to say that we call the anti-re-rank strategy. So that means that between, let's say, this model and this model, we are going to see that the decision boundary doesn't change too much, right? So just because it doesn't change too much, we are going to say, okay, in the next moment, well, we need to ask for some unlabeled data to label, then we can almost show that those informative data will be the same. So which means that we don't need to do the uncertainty computation, and also we don't need to do the re-ranking. Here is another strategy that we propose, is that we use actually the hierarchical strategy, so that to separate between, let's say, some data could be very important or some data could be not so important. Okay, so for those data not likely to be, let's say, informative to be included, or that later we want to ask their label information from Oracle, is will be, okay, for those data, actually we just perform some approximate computation, such as that actually we perform PCA to project them to low dimensional space. In low dimensional space, if they are closer to the boundary, meaning that their uncertainty will be high, then maybe we push to the upper level, so that they will be likely, maybe they will potentially chosen to be the one that we need labeling information. So other than that, maybe we just make it to be stay in the low layer, okay, and almost like we don't need their label information. So this strategy is that called the multi-layer pooling. Okay, so talk about multi-layer pooling. Actually, we consider that we want to make the number of unlabeled data to be considered as small as possible, meaning that if we use a hierarchical structure, then the amount of data we need to compute their uncertainty will be quite small. And at the same time, we also consider the dimensionality, meaning that if we talk about, let's say, it will be a lot of data that we need to compute the uncertainty, maybe we consider in low dimensional space, so that we only consider several dimensions, the computation will be easy. On the other hand, if there will be some data that we need to consider a lot of dimensionality, maybe there will be only a few of them. They are like quite likely to be the chosen one, so that the informative data, so that maybe we can spend more time on it because it's just a small set. So combine these two strategies and we can have a very good result. Maybe let's just move on to talk about the evaluation. So we have the data that we call the MNIST data. It's a well-known data set that consists of the digit recognition. Okay, so the result is like this. Then if we use the two strategy, either we use MLP, the multi-layer pooling, or we use the anti-re-rank strategy, and both can reduce the time to be either will be 1/3 or maybe less than 1/4 of the original result. The original result takes like more than 9 hours, and actually after the reduction, we only need 3 hours or maybe 1 hour, less than 2 hours to finish. And if we combine both strategies, we can even make computation even shorter. So combine the both research, if we have already talked about that the time can be deducted with quite a lot of amount. And if we talk about the accuracy, and we can see that between different strategy, and if we either we combine or if we use one of the strategy, we can have a very good accuracy. Okay, compare almost the same when we have with the original active learning research. So ensure that what we mean by that is that we propose very efficient computation, and when we stack computation, even that just 1/3 or 1/4 of the whole the original computation, we can still enjoy almost the same accuracy. So when we move on to talk about interactive machine learning, and we talk about we need to consider the human factor in this case. So in this case, we all talk about the realization in smart factory. In this case, actually, we need to consider the dynamicity, because for different workers, and then may have a different, in different moments, they may have a different skill, can perform in different levels. Okay, and also we can talk about that between human and machine, they may all have, they both can have a different roles, such as that for the worker side, they may have the master, they may have novice. For the machine side, the machine can perform like a teacher, or like students, or even guardian angels to human. From time to time, we use this to illustrate the difference, or maybe what we want to focus on in the active machine learning. So between the human and machine, actually in this case, the human may be considered a master or a novice. When we consider the right-hand side between the master and the machine, actually the master will continue to provide the label information to human. For instance, the master will continuously provide some label information to machines, meaning it's like maybe we can consider it's the regular, the active learning scenario. But what we want to say more is that between the machine and the novice, and actually we consider that the machine may teach the novice when they are not good at this some task. Okay, so the machine will help the master to teach novice, even sometimes when the master will not be so available. Okay, so we can talk about, okay, before now we work more on this part, such as between master and machine, that we consider that maybe the active learning research will be in this part. Okay, on the other hand, in the rest of this project, maybe we want to put more focus on the second part, that is between machine and novice. Okay, so the machine will know how to teach novice in some efficient way, so that the novice will learn well in short period of time. Okay, so what we call between, let's say, the machine can teach the novice, that we call the machine tutoring. The machine tutoring will provide a learning set for a novice to learn in a short period of time. And also, the machine can dynamically adjust according to different novice ability, okay, or maybe learning curve, okay. And also the machine will keep track what the beginner's performance at different moments. We can say that in this framework, the machine will act as a partner or students to masters. But what we want to put more focus is that the machine will also can be considered as a substitute of master, or maybe teachers to novice. So actually, we have some partial result that we want to focus on, that we call the skill learning, and that will be quite often that we can see this useful in the smart factory scenario. So we want to say, okay, between a machine and a novice, okay, machine will help the master to transfer something to novice, to transfer some ability to novice. So how to transfer? Actually, the ability transfer may include the knowledge transfer or skill transfer. Okay, other than the knowledge transfer, actually the skill transfer is as important as many others in a smart factory environment. So the knowledge transfer, maybe we want to say the knowledge transfer could be more related to interactive dialogue learning, and in our part we want to focus more on the skill transfer. Okay, and we use the Hsing-Kuo drum playing as an example to realize the scenario of skill transfer. So we talk about this game. Actually, this game that maybe some people play this before, that we have music coming and we need to listen to music and check the when that we need to hit the drum. Okay, so we hit the drum maybe within a certain period of time, then we got a good score. Okay, so here is the scoring as time goes by, right? So when we have, let's say, starting from the time that we have the music starts, okay, then we continue to collect more score. Okay, after when the music finish, maybe we'll receive the final score. Okay, so in different moment, then sometimes the music could be move very fast or move very slow, so people may react differently. Okay, so we use some sensor to record that for different users when they play the game. Okay, what kind of performance they may have. So here is the sensor that we built. We put in our elbow to record. So when we hit, okay, the sensor will give us the signal, and then they will know that, okay, for different people and the right hand and left hand, they know that how we perform, how we play this game. For this experiment, actually, we have collected several sensory data, and basically they are all what we are familiar with. It's just like the acceleration sensor and gyro sensor, etc. Right? So we can use. Actually, we don't use the temperature or maybe humidity, those kind of sensor, and we focus on the acceleration and the gyro sensor according to different axes. So using those sensory information, we hope that we can catch the different users' performance. So here, just show you some kind of data that we have collected. So maybe if we focus on this part, that will be the orange one will be the left-hand side. The orange one will be the right hand for the right hand playing, and the blue one will be the left hand playing. And actually, we're going to see that for different music and different people, and they may perform different for their left hand side and the right hand side. We're going to see that, okay, based on this sensory data, maybe we can guess that for different people, they may good at a right hand side or left hand side. Okay. So currently we have thinking about a plan as 1, 2, 3. So the first step is to be able to reproduce the scoring that was provided by the game. Okay, so hopefully based on the sensory data, we can pick up what kind of score only with the sensory data. Then we talk about the second step is that, okay, between different people's playing, and then we can suggest based on some rules. Okay, we can suggest a rule base. We can suggest some rules for the machine tutoring, such that we can tell the novice, okay, the beginners, when they started to learn how to play this game, okay, what they should put more focus or what they should maybe do more exercise. Okay, so those rules will help in two situations, such as, okay, maybe we are going to find a way to achieve high scores. On the other hand, we can go beyond that. That is that, okay, maybe we can try to mimic somebody's playing, okay, such that they may play quite well, but even many of them received similar scores. Okay, the third step is to move on to talk about the data-driven tutoring, means that when we based on only the sensory data, hopefully we can see the different styles of playing, okay? And maybe they can give us different score, maybe they give us a similar score. So how to mimic someone's playing? So that's what we want to focus on for these few days. Okay, actually, in these few days, we also have two other related research. That the first one is actually we have a real human tutoring applied in a real smart factory. Hopefully, after a while, then maybe we can share the experience with you guys. Okay, the second one is that we want to deploy interactive machine learning scenario in semi-automatic driving scenario, such that when we are driving, then the some system or machine can give us, okay, where that we can put more focus on, okay, and certain in different situations, such that when we go in near the cross, we need to see the traffic from both sides, etc. Right? So where that we can put more attention is that one of the red hot topics in the autonomous driving these days. We also want to use the interactive machine learning to do some research on this part. So that's basically the my report for that we have talked about continuous sensing monitoring. Actually, we have a few publications in these few years, and starting from that, and we also have some work on active learning, and to move beyond that, and we will focus more on the human tutoring, and in these few days, maybe in this year and next year, especially, hopefully we can deploy the framework in smart factory environment. Thank you.